Exploring the Cosmos, a comprehensive analysis of 60 years of lunar probe missions. Introduction. Since the dawn of the space age in 1957, lunar probe missions have played a pivotal role in humanity's quest to explore outer space. The Moon, Earth's closest celestial neighbor, has served as both a destination for human exploration and a platform for scientific research that informs our understanding of the solar system. Over the last 60 years, various space agencies, notably NASA, have launched missions that have transformed our knowledge of the Moon's geology, potential resources, and its role in the broader context of planetary science. Historical context of lunar exploration. The space race ignited by the launch of Sputnik 1 by the USSR on October 4, 1957 marked the beginning of a new era in human exploration. This competition between the United States and the Soviet Union extended beyond Earth and into the cosmos, with both nations racing to achieve significant milestones in space exploration. The first major U.S. initiative aimed at the Moon was NASA's Ranger program in the 1960s, which included a series of spacecraft designed to crash land on the lunar surface and transmit images back to Earth. Key lunar missions. 1. Ranger missions 1961 to 1965. The Ranger spacecraft provided the first close-up images of the Moon, helping to determine the best landing sites for future missions. Ranger 7 in particular transmitted over 4,000 images of the lunar surface. 2. Lunar Orbiter missions 1966 to 1967. Following the Ranger missions, the Lunar Orbiter program mapped the Moon in detail, identifying potential landing sites for Apollo missions. These missions significantly increased our understanding of the Moon's topography and geological features. 3. Apollo missions 1968 to 1972. The Apollo program culminated in Apollo 11's historic landing on July 20, 1969. When astronauts Neil Armstrong and Buzz Aldrin became the first humans to walk on the lunar surface. The Apollo missions returned a total of 382 kilograms of lunar rocks and soil, which have been invaluable for scientific research. 4. Lunar Reconnaissance Orbiter LRO 2009 present. Launched in 2009, the LRO has provided high-resolution maps of the Moon's surface, aiding in the identification of landing sites for future missions and providing data on the Moon's topography, mineralogy, and potential resources. 5. Recent missions. More recent missions, including China's Chang'e program and India's Chandrayaan missions, have further expanded our knowledge. Chang'e 4, which landed on the far side of the Moon in 2019, marked a significant milestone in lunar exploration. Technological advances in lunar exploration. The evolution of spacecraft technology has been central to the success of lunar exploration. Early missions relied on relatively simple designs, while modern probes utilize advanced technologies, including high-resolution imaging. The LRO employs sophisticated cameras and sensors to capture detailed images and data about the Moon's surface. Robotic exploration. Recent missions leverage robotics to conduct experiments and collect data without human presence, reducing risk and costs. Landing technologies. Improved landing technologies allow for safer and more precise landings on the lunar surface. Scientific discoveries and contributions. Lunar probe missions have led to significant scientific discoveries, including geological insights. Missions have revealed the Moon's geological history, including volcanic activity and impact cratering, which are crucial for understanding both the Moon and Earth's formation. Water ice reserves. The discovery of water ice in permanently shadowed craters has profound implications for future lunar habitation and exploration. Understanding planetary processes. Studies of the Moon serve as a proxy for understanding processes that occur on other celestial bodies, including Mars and asteroids. Future of lunar exploration. As we move further into the 21st century, NASA and other space agencies are planning ambitious missions aimed at sustainable lunar exploration and the eventual human exploration of Mars. Key future initiatives include Artemis program, aimed at returning humans to the Moon by the mid-2020s. The Artemis program focuses on exploring the lunar South Pole, which is believed to contain significant water ice deposits. International collaborations. Future missions are expected to involve collaborative efforts between various countries and commercial partners, expanding the scope and scale of lunar exploration. Conclusion. The last 60 years of lunar probe missions have laid the groundwork for humanity's future in space. Each mission has contributed to our understanding of the Moon and its significance within the solar system, providing essential data that will inform future explorations. The Moon remains a critical stepping stone for human exploration beyond our planet, and as technology advances, our ability to explore and utilize lunar resources will only improve. Through ongoing research and international collaboration, we continue to push the boundaries of what is possible in our quest to explore the cosmos. The content regarding lunar probe missions and the broader history of space exploration contains several counterintuitive points that challenge common perceptions. Here are the most notable ones. 1. Technological progress in human exploration. A common belief is that human exploration of the Moon and Mars is primarily driven by the presence of astronauts. However, the significant advancements in robotic missions, such as those conducted by the Lunar Reconnaissance Orbiter (LRO) and various Mars rovers, have provided critical data that inform human missions. The idea that robots can gather more comprehensive data than humans is a counterintuitive perspective, as many people assume that human presence is essential for exploration. 2. Role of competition in space exploration. The narrative often emphasizes the competitive nature of the space race, particularly between the US and the USSR, portraying it as a straightforward contest for supremacy. However, the actual history reveals that both superpowers utilized a substantial amount of shared knowledge and expertise from German scientists post-World War II, complicating the notion of competition. The fact that both sides capitalized on similar technological advancements and human resources illustrates the collaborative aspect of what is often deemed a rivalry. 3. Impact of historical context on technological development. While it is widely acknowledged that the space race spurred technological advancements, it is less recognized that many of the early engineers and scientists involved had dubious pasts, such as Wernher von Braun's affiliations with the Nazi regime. This creates a paradox where the progress in space technology was significantly aided by individuals with controversial backgrounds, raising ethical questions about the intersection of morality and scientific progress. For public perception of space missions, the assumption that successful space missions are predominantly celebrated by the public overlooks the fact that many missions, especially robotic ones, receive less media attention compared to human spaceflight. For instance, the LRO and OSIRIS-RX missions have made groundbreaking discoveries. Yet they do not capture the public's imagination in the same way as manned missions do. This disparity suggests a counterintuitive relationship between public interest and scientific achievement. 5. Future collaboration versus competition. The article discusses how NASA's future endeavors are shifting away from a race-driven mentality to one of collaboration with commercial partners and international agencies. This represents a significant departure from the historical context of space exploration, where competition was a primary motivator. The idea that collaboration can yield better results than competition is a counterintuitive shift in the philosophy of space exploration. 6. Misconceptions about lunar resources. While many assume that the Moon's resources are scarce and of little value, recent missions have suggested otherwise, revealing potential resources like water ice at the lunar poles. This challenges the perception that the Moon is just a barren rock and underscores the strategic importance of lunar exploration for future human missions to Mars and beyond. 7. The unity of science and politics. The intertwining of science and geopolitics in space exploration is often underappreciated. The article notes how the space race was not just a pursuit of knowledge but also a means of soft power during the Cold War. The idea that scientific exploration can be a tool for political leverage is a surprising insight that complicates the narrative of pure scientific inquiry. 8. Underrepresentation in space programs. There is a common narrative that the space program was predominantly a white male endeavor. However, the contributions of women and people of color such as Katherine Johnson and others played a crucial role in NASA's successes. The recognition of these contributions challenges the stereotype of a homogeneous group of space pioneers and highlights the diverse efforts that have shaped space exploration. 9. Misunderstanding of space missions goals. Many perceive space missions as solely focused on exploration or scientific discovery. However, the strategic implications of these missions, such as establishing a foothold for human habitation on the Moon to facilitate future Mars missions, indicate that the goals are often more complex and politically motivated than they appear. These counterintuitive points illustrate the multifaceted nature of space exploration, challenging oversimplified narratives and encouraging a deeper understanding of the historical, technological, and ethical dimensions of humanity's journey into space. Important overlooked content in the report on lunar probe missions. 1. Political and competitive context of the space race. The report touches on the competitive nature of the early space exploration efforts, particularly during the Cold War. However, it often underplays the significance of how political motivations shaped the direction and funding of lunar probe missions. The space race was not merely about scientific progress but also a critical aspect of national pride and technological demonstration against geopolitical rivals. Understanding this context is essential to grasp why certain missions were prioritized and the socio-political ramifications of these endeavors. The race for the Moon symbolized not just technological prowess but also ideological superiority. 2. Role of international collaboration. While the report emphasizes NASA's achievements, it could benefit from a deeper exploration of the role of international collaboration in lunar exploration. For instance, the Lunar Reconnaissance Orbiter and other missions have involved partnerships with international space agencies. The significance of these collaborations lies in the pooling of resources, expertise, and data, which enhances scientific understanding and reduces costs. As future lunar missions aim for sustainability, international cooperation will be pivotal in establishing a long-term human presence on the Moon and advancing towards Mars. 3. Technological innovations and their broader implications. The technological advancements mentioned, such as the Lunar Reconnaissance Orbiter (LRO) and Mars rovers, are often highlighted for their scientific contributions. However, what many may overlook is how these innovations have broader implications beyond space exploration. Technologies developed for space missions have found applications in various fields, including telecommunications, materials science, and even medical technologies. For example, advancements in imaging technologies used for lunar mapping have been adapted for Earth-based medical imaging. Recognizing these cross-disciplinary impacts underscores the value of investment in space exploration. 4. Environmental considerations in lunar missions. The environmental impact of lunar exploration is a crucial aspect that is frequently overlooked. As missions aim to utilize lunar resources for future human habitation, concerns about contamination and the preservation of lunar ecosystems become significant. The report could elaborate on the need for sustainable practices in lunar exploration to prevent irreversible damage to the Moon's environment. This is particularly relevant as discussions about mining lunar resources intensify, raising ethical questions about exploitation versus preservation. 5. Public engagement and perception. The report primarily focuses on the missions and technological achievements but does not delve into the public's perception and engagement with these missions. The emotional and inspirational aspects of space exploration contribute significantly to societal support and funding. Understanding how public interest fluctuates in response to major milestones in lunar exploration can inform future outreach and education efforts. Engaging narratives about humanity's journey to the Moon can galvanize support for ongoing and future missions. 6. Scientific legacy and future exploration. There is a tendency to focus on current and upcoming lunar missions without adequately addressing the scientific legacy of earlier missions. The data collected from Apollo missions and subsequent lunar probes laid the foundation for contemporary lunar science. Exploring how these historical missions inform current research strategies and goals provides valuable context for understanding the evolution of lunar exploration. It also highlights the continuity in scientific inquiry and the importance of historical knowledge in shaping future objectives. 7. Ethical considerations in space exploration. The ethical dimensions of lunar exploration are often underrepresented in discussions. As humanity prepares for a sustained presence on the Moon and beyond, ethical considerations regarding the rights to explore and utilize extraterrestrial environments must be addressed. This includes deliberations on ownership, resource utilization, and the potential impact on any microbial life that may exist. Engaging in these ethical discussions is crucial for creating frameworks that govern responsible exploration and usage of lunar and planetary resources. 8. Impact of robotic missions on human exploration. The report tends to separate robotic and human missions as distinct categories but does not adequately discuss the interdependence of these efforts. Robotic missions have paved the way for human exploration by providing critical data on lunar conditions, resource availability, and potential hazards. Highlighting this relationship can help frame future missions as collaborative efforts where robotic and human exploration are integrated rather than sequential. 9. Technological accessibility and innovation. While NASA's advancements are celebrated, the report overlooks the significance of technological accessibility. Many innovations developed for space exploration can and should be adapted for use on Earth, particularly in underserved communities. Initiatives that promote accessibility to space technology can foster innovation in various sectors, enhancing local problem-solving capacities and sustainability efforts. Encouraging a broader discourse on how space innovations can benefit Earth communities is crucial for inclusive technological development. 10. The role of women and underrepresented groups in space exploration. Although the report touches upon contributions from various demographics, it does not delve deeply into the pivotal roles played by women and underrepresented groups in the history of space exploration. Their stories and contributions are often marginalized in mainstream discussions. Elevating these narratives can not only provide a more comprehensive view of space exploration history but also inspire future generations from diverse backgrounds to pursue careers in STEM fields. Significance of the overlooked content. The significance of these overlooked aspects lies in their potential to reshape the narrative surrounding lunar exploration. By integrating political, ethical, and social considerations into the discourse, stakeholders can create a more holistic understanding of space missions. This comprehensive view can foster public engagement, encourage ethical practices, and promote international collaboration, ultimately enriching humanity's approach to exploring the cosmos. Moreover, recognizing the interconnectedness of technological advancements, environmental stewardship, and diverse contributions can stimulate innovation and inclusivity in the space sector. As we stand on the brink of renewed lunar exploration, these discussions are not merely academic, they are essential for guiding the future of humanity's endeavors in space, ensuring that exploration is conducted responsibly, ethically, and inclusively. 1. Technological advances in space exploration. The evolution of lunar probe missions over the past 60 years has been marked by significant technological innovations. From the early Ranger and Lunar Orbiter missions in the 1960s to contemporary missions like the Lunar Reconnaissance Orbiter (LRO), advancements in spacecraft technology have allowed for unprecedented exploration of the Moon. These innovations not only enhance imaging and data gathering capabilities but also pave the way for new exploration techniques, such as the use of robotic systems for mining lunar resources. This technological trajectory is pivotal in supporting future missions and fundamentally alters our approach to space exploration. 2. Scientific discoveries and knowledge expansion. The data collected from lunar probe missions has vastly expanded our understanding of the Moon's geology, history, and potential resources. Findings from missions like Apollo 11, which collected lunar samples, and the LRO, which produced detailed topographic maps, are crucial for planning future human habitation on the Moon. These missions have revealed insights into the Moon's formation and its relationship with Earth, contributing to broader planetary science and influencing theories about the solar system's evolution. The ongoing analysis of lunar samples and data continues to support scientific inquiry and discovery. 3. Strategic importance of the Moon for future exploration. The Moon serves as a critical stepping stone for human exploration of Mars and beyond. The strategic importance of lunar missions lies in their potential to test technologies and life support systems necessary for future human missions to more distant destinations. NASA's Artemis program aims to establish a sustainable presence on the Moon, enabling astronauts to conduct research that informs the challenges of living on Mars. This focus on the Moon reflects a shift in exploration strategy, emphasizing the Moon as a launchpad for deeper space exploration rather than merely an endpoint. For international collaboration and the commercial space sector, the future of lunar exploration is increasingly characterized by international collaboration and partnerships with commercial entities. Unlike the competitive nature of the original space race, current and upcoming missions reflect a cooperative approach, encouraging joint efforts among countries and private companies. Collaborations such as the Lunar Gateway project, which involves multiple international partners, illustrate this trend. Additionally, the rise of commercial spaceflight companies contributes to the democratization of access to space, fostering innovation and reducing costs associated with space exploration. This collaborative framework is essential for expanding the scope and scale of lunar missions, making ambitious exploration goals more achievable. 3 famous historical cases similar to lunar probe missions. 1. Apollo program 1961 to 1972. The Apollo program, developed by NASA, aimed to land humans on the Moon and bring them safely back to Earth. It was a monumental achievement in human space exploration that began with President John F. Kennedy's 1961 challenge to land a man on the Moon by the end of the decade. The most famous mission, Apollo 11, successfully landed astronauts Neil Armstrong and Buzz Aldrin on the lunar surface on July 20, 1969. They collected samples and conducted experiments before safely returning to Earth. The Apollo program not only demonstrated the capabilities of human spaceflight but also provided extensive scientific data about the Moon's geology and environment, influencing future lunar exploration and paving the way for international collaboration in space research. 2. Voyager missions 1977-present. The Voyager program consists of 2 spacecraft, Voyager 1 and Voyager 2, launched by NASA in 1977. These probes were designed to explore the outer planets of the solar system and have provided invaluable data about Jupiter, Saturn, Uranus, and Neptune. Voyager 1 is currently the farthest human-made object from Earth, having entered interstellar space in 2012. The missions have contributed significantly to our understanding of planetary atmospheres, magnetic fields, and the characteristics of the moons of these gas giants. The golden record, a phonograph record included on each spacecraft, was intended to communicate the story of our world to extraterrestrials, illustrating humanity's desire to connect with the cosmos. 3. Mars exploration rovers 2003-present. The Mars Exploration Rover program, comprising Spirit and Opportunity, was launched by NASA in 2003 to explore the Martian surface. These rovers were designed to search for signs of past water activity and assess the planet's potential for habitability. Both rovers exceeded their expected operational lifetimes, providing a wealth of data about Mars geology and climate. Opportunity, for example, operated for nearly 15 years, far surpassing its initial 90-day mission. The data collected by the rovers have been crucial for understanding Mars' history and its potential for life, significantly influencing future Mars missions and the ongoing quest for human exploration of the Red Planet. Future outlook, predictions for lunar probe missions and beyond. As we approach the next decade in lunar exploration and beyond, the trajectory of space missions, particularly those focused on the Moon, appears promising and transformative. Based on historical trends, advancements in technology, and the evolving landscape of international collaboration, we can make several key predictions regarding future lunar probe missions and their implications for broader space exploration. 1. Increased international collaboration. The future of lunar exploration is likely to be characterized by unprecedented levels of international collaboration. Space agencies worldwide, including NASA, ESA, European Space Agency, CNSA, China National Space Administration, and ISRO, Indian Space Research Organization, are increasingly recognizing the benefits of working together. This trend will culminate in joint missions, shared resources, and collaborative research initiatives aimed at exploring the Moon and beyond. For instance, missions like NASA's Artemis program, which aims to land astronauts on the Moon by the mid-2020s, are expected to involve international partners in various capacities, enhancing both scientific output and diplomatic relations. 2. Sustainable lunar presence. Predictions suggest that by the late 2020s or early 2030s, human presence on the Moon will transition from short-term missions to a more sustainable long-term outpost. NASA's Artemis program envisions the establishment of a lunar base at the lunar South Pole, where astronauts will conduct research test technologies vital for Mars exploration and study the Moon's resources, including water ice. This lunar outpost will serve as a critical testing ground for technologies necessary for future human missions to Mars and beyond. 3. Technological advancements in spacecraft and robotics. The next wave of lunar missions will likely be marked by significant advancements in spacecraft and robotic technologies. Innovations such as autonomous navigation systems, advanced communication networks, and enhanced propulsion methods will make missions more efficient and cost-effective. For example, the use of small satellites and landers equipped with advanced AI will improve the ability to conduct detailed surveys of the lunar surface, identify resources, and optimize mission logistics. Technologies developed for lunar exploration will also find applications in other planetary missions, including those aimed at Mars and asteroids. 4. Resource utilization and economic opportunities. As lunar exploration progresses, the focus on resource utilization will intensify. Future missions will likely prioritize mining lunar resources, such as water ice and rare minerals, which could support human habitation and fuel production. This shift towards in situ resource utilization (ISRU) will not only reduce the costs associated with transporting supplies from Earth but also lay the groundwork for a lunar economy. Private companies are expected to play a crucial role in this economic landscape, offering services ranging from transportation to mining operations. 5. Scientific discoveries and astrobiology. The Moon is a treasure trove of scientific knowledge, and future missions will continue to unlock its secrets. Enhanced instruments aboard lunar probes will allow for in-depth studies of the Moon's geology, history, and potential for harboring life. Additionally, missions focusing on the Moon's South Pole, where water ice is abundant, will provide critical insights into the history of water in the solar system and its implications for astrobiology. These discoveries will inform our understanding of life's potential beyond Earth, particularly in harsh environments. 6. Expansion of commercial space sector. The commercial space sector will play an increasingly significant role in lunar exploration. Companies like SpaceX, Blue Origin, and others are expected to provide launch services, transportation to lunar bases, and even develop technologies for lunar habitats. As public-private partnerships flourish, the costs of lunar exploration will decline, making it more accessible for scientific institutions and international entities. The commercialization of lunar missions could lead to new markets in space tourism, lunar research, and even entertainment, further driving public interest and investment in space exploration. 7. Interplanetary missions and Mars preparation. The advancements made through lunar exploration will serve as a springboard for interplanetary missions, particularly those targeting Mars. By the late 2030s or early 2040s, we may see human missions to Mars facilitated by the technologies and experiences gained from lunar operations. The Moon will act as a testing ground for life support systems, radiation shielding, and other critical aspects of long-duration space travel. Additionally, lunar missions will help refine strategies for landing on, living on, and returning from Mars, ultimately paving the way for human expansion into the solar system. Conclusion. The future of lunar probe missions is poised to be a dynamic and exciting chapter in space exploration. With a focus on international collaboration, sustainable presence, technological innovation, and resource utilization, we are on the brink of a new era that not only aims to deepen our understanding of the Moon but also lays the foundation for the exploration of Mars and beyond. As we harness the knowledge and resources from our lunar endeavors, the potential for discovering new worlds and understanding our place in the universe will only expand, inviting future generations to dream bigger and reach further into the cosmos.